understanding binary, or how to convert binary, which is the way computers talk, to decimal, which is the way that we deal with numbers, and decimal to binary, pertains to a lot of different aspects of, as I just mentioned, networking. So to begin with, binary, as the name implies from bi, is what we call a base 2 system. More commonly, we used a base 10 system, decimal. Now, this means that we have 10 possibilities for every place value. We have between 0 and 9. You add that up, there are 10. Now, with binary, there's only 2 options, either 0 or 1. So we can either have a single 0 or a single 1. And that's what we call a binary digit or a bit. So the binary number has place markers that are similar to the base 10 system. For instance, if we have a decimal base 10 numbering system, the second place mark designates the tens. If we imagine that there's a period or a decimal right there. The third designates the hundreds, and then we move to thousandths and 10,000ths and 100,000ths and so on and so forth. And in each one of these, we can have anywhere from 0 to 9. And that's 10 options in each one of those spots. Now, in a base 2 numbering system, which is binary, we have only 2 options, a 1 or a 0 in either one of those places. And in computers, especially in a lot of IP addressing, we really deal with the difference between 8 different places. So we're going to call these 8 an octet. So this 8-place binary digit is referred to as an octet because there's 1, 2, 3, 4, 5, 6, 7, 8 of them. And you'll see these numbers pop up over and over again. So this is really as far as you need to know for binary, although you can go even further. So if we look at this octet from the right side to the left, the first place mark is what we call 2 to the 0 power, right? If we were talking about this in tens, this would be the ones place. Why? Because it's 10 to the 0 power, which is ones. Anything taken to the 0 power is 1. Next, we have 10 to the first power, which is going to equal 2. If you recall, we call this the tens place. 10 to the 1 power means 10 by itself is 10. Then we have 10 to the second power, which is 4. And if you recall, in decimal, this is 10 to the second, which would be 10 times 10, which is 100. You can see where this is going. So 2 to the third is 8. 2 to the fourth equals 16. 2 to the fifth equals 32. 2 to the sixth equals 64. And 2 to the 7 equals 128. So each one of these place markers is equivalent to this number, whether it's turned on or off. Now, to help clarify this a bit, each place here has one of 2 options, correct? Because it's base 2. If it's off, that means it's a 0, as you see right here. And the number means it's not being counted. So we don't count any of these numbers we've just calculated. So if all the bits are off, that means that we have a number of 0. If all of the bits are on, then this means we add each of the numbers together. So we get 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, which equals 255. Now, believe it or not, you can create any combination of numbers from just binary. You don't need decimal. And we're going to see that in just a second. So, for example, let's say the binary number is 000000111. Well, in this case, the 128, 64, 32, 16, and 8 bits are all off. The only ones that are on are 4, 2, and 1. And if we add those together, 4 plus 2 plus 1, we'll get 7. 4 plus 2 is 6, plus 1 is 7. If we take another number, say 011001110, then this is going to equate to 102. Why? 64 plus 32 equals 96, plus 4 equals 100, plus 2 equals 102. So it's pretty simple. You just take the number with the ones under it and add them together. So now that we've converted binary into decimal, a number that we all know, let's go ahead and see if we can convert the other way, decimal to binary. Now, for this process, we're going to use the same exact chart that we just saw with the binary conversion. And this chart is going to help us visually represent all the binary digits, which is why I like it, and they're placeholders, and it makes it a lot easier. So, for decimal to binary, we simply go from left to right and break down the number until we reach the 0. So let me break that down a little bit. For instance, if we take the number 128, right, this is pretty easy to convert. We plug it into this chart. How many times does 128 go into 128? One time. If we take all the others and we subtract them, we're going to have 0, right? Because now 128 minus 128 is 0. That leaves us with our binary number 1000000, which is equivalent to 128. Now, if we take a look at a different number, let's say the number 218, this is going to take a little more math. Does 128 go into 218? It certainly does. So 218 minus 128 has a remainder of a certain amount, which is 90. Does 64 go into 90? It does. We now have a remainder of 26. Does 32 go into 26? No, it doesn't, so we put a 0. Does 16 go into 26? Yep, it does, which leaves us with a remainder of 10. Does 8 go into 10? It does, which leaves us a remainder of 2. Does 4 go into 2? It does not, so that leaves us with 0. We still have our 2. Does 2 go into 2? Yep. And then do we have anything left over? Nope, we're at 0 now, so we have 0. If we now add all those up, this is our binary number 110111010. Now, while this might seem like a fairly long process, it's important to understand how this works, because when we get into subnetting, it's really going to become important so we can have a better understanding of networking in general.